Next up, we're going to try out some integrals that are going to involve making use of logarithms. First example that I have for you is going to be more than just logarithms. We have the indefinite integral of x squared plus 1 over x, all times dx. This one, we're actually going to apply the distributive property first. We're going to distribute that denominator to both of the terms that are in the numerator and simplify algebraically before we try to take an integral. X squared over x reduces down to x, and 1 over x is just 1 over x. Now, the x can be integrated using the power rule. We'll call that 1/1/2 of x squared. And the 1 over x will integrate into the natural log of the absolute value of x plus c. We're going to see that integral show up a couple more times as we work through our examples. Next up, I wanted to try out the sine of 2x divided by 1 plus the cosine squared of x. There are actually a couple different substitutions that will sort of push you in the right direction on this one. I'm going to go for the most straightforward one, as you will see in just a moment. So this will be 1 plus the cosine squared of x. That's what I'm going to select for my u. Du would then be the derivative of this. Now, a derivative of 1 is simply going to be 0, and derivative of cosine squared of x will require the chain rule. This will be 2 times the cosine of x times the derivative of the cosine of x. That'll be the negative sine of x dx. Now, there is an identity that can be used here, so I will ask you to recall with me that the sine of 2x is actually equal to 2 times the sine of x times the cosine of x, referred to as a double angle identity from back in trigonometry. Well, you'll notice here that we have a 2, and we have a sine of x, and we have a cosine of x. The only thing that we're missing is the negative. So what we can do here is take the 2 and the sine of x and the cosine of x, put them together and call it the sine of 2x, and move this negative over to the other side. So that when we make a substitution on the sine of 2x times dx, we can simply turn that into negative du. This will turn the integral into negative du divided by u. Now, with that in mind, the negative is a constant multiple. We'd be left with 1 over u times du. And this will be the negative natural log of the absolute value of u plus c. Technically speaking, though, the absolute value is not necessary in this case due to the fact that 1 plus the cosine squared of x is a quantity that is always positive. Boy, I really hope that this has been working, because I just got a notification from my tablet that maybe things weren't great. Oh well, we'll review this afterward and see how it goes. Finally, one more that I wanted to try out. This is going to be something that shows up pretty frequently in future classes. This is going to be the integral of the tangent of x dx. Now, there are 2 separate ways to evaluate this integral, and I wanted to talk about both of them. One of them is going to be the quotient identity from back in trigonometry, which puts this into the form of something where we could do a substitution on the bottom and see its derivative on the top. We could let u be equal to the cosine of x, therefore du would be equal to the negative sine of x times dx. Then we could do essentially the same thing as what we did on the previous problem and say then that the sine of x dx is equal to negative du. This allows us to take the sine of x times dx and transform that into a negative du. Your denominator would simply be u. Based on what we saw in the last problem, that would be the negative natural log of u plus a constant, or the negative natural log of the absolute value of the cosine of x plus a constant. I did mention that there are 2 different ways to try this problem out, so I would like to show you the other way. This one is just sort of a, well, I don't understand where that came from kind of problem. Well, where it comes from is not nearly as important as how it works. So what I'm going to do is I'm going to turn this into a nice big fraction with the tangent of x over here. I'm then going to multiply the top and bottom of this fraction by the secant of x. To which you would probably pose the question, well, why do we do that? The answer is, well, short answer is because it works. We're going to let u be equal to the secant of x, because that's what's in our denominator. Then, as if somebody waved a magic wand, when we calculate our differential, we see that du is equal to the secant of x times the tangent of x times dx, which Magically, that is our numerator. Therefore, we can turn this into du divided by u. Integrating this, we'll get the natural log of the absolute value of u plus c, which would be the natural log of the absolute value of the secant of x plus c. Now, comparing that with our previous result, you'll notice that the results are similar, but not quite the same as each other. I do want to point out, though, that there is a property of logarithms that says that if you have a coefficient, you can turn that into a power. Now, the cosine of x raised to the negative 1 power is asking for the reciprocal of the cosine of x, which by some amazing coincidence happens to be the secant. So you can consume this negative sign to turn that into the reciprocal of the cosine, and everything works out just peachy keen.